Good morning, everyone. So welcome to the 12th Electron Devices and Solid-State Circuits online seminar. This seminar is also part of the Hong Kong University of Science and Technology Academy of Continuing Education. Today, we are very honored to have Professor Chan Li here. He is currently an assistant professor at the Department of Electrical and Electronic Engineering from the University of Hong Kong. He is working on analog and neuromorphic computing accelerators based on post-CMOS emerging devices, memristors, for example. So this device will be used for efficient machine, deep learning, network security, signal processing, etc. Before that, he spent 2 years at the HP Labs in Palo Alto, California. He obtained his PhD degree from University of Manchester, University of Massachusetts Amherst, and the bachelor and master degrees from Packard University. Without further ado, let's welcome him to give the seminar. Professor Li, you can start now.
Okay, thanks for Professor Shao Qiming's great introduction. Good morning, everyone. This is Chan Li, and as introduced by Professor Shao, I joined the University of Hong Kong in the Department of Electrical and Electronic Engineering about 6 months ago. And my current interests including like neuromorphic computing and deep learning accelerators based on emerging nano-electronic device. My topic today is about the defect tolerant in memory analog computing with CMOS-integrated nanoscale crossbars. But before my talk, I want to point it out that some of the work was done when I was with Hewlett Packard Labs and UMass Amherst. Therefore, I would like to especially thank my PhD advisor, Professor Chang Fei-Xia, and close collaborator, Professor Joshua Yang, and my manager, Dr. Zhang Strakin at Hewlett Packard Labs. Can you hear me clearly? I just want to make sure that.
Yes.
Okay, cool. So here's an overview of my talk. First of all, I'm gonna introduce a little bit of background. And second, I wanna introduce the platform, which is a CMOS integrated nanoscale crossbar. In this kind of the integrated system, we found a little bit a different phenomenon than the a non-integrated version, so that those features of the device can enable some applications out of it. And because this is a very new device, so we found this device sometimes have defect, so that those defects cause some unexpected computing error. So we come up with 2 solutions to solve those problems. One is we come up with a new analog error correcting code to detect and correct some computing error exceeds a predefined threshold. And the second method is to use in-situ training to make the network adapt to those defects. And I will finalize the talk with a summary. And I think, as Professor Shaw introduced, feel free to ask questions in the chat box so that I can answer the questions maybe after the talk. So the topic today is about analog computing, because analog computing is a little different from digital computing, but this analog computing is not new technology at all. In fact, it's probably the earliest form of computing, because we are living in the analog world, and it's more intuitive for us human beings to compute in the analog domain. For example, our ancestor began to compute the position of stars with some mechanic computing units. And what's more, even the earliest neural network was built directly by emulating the physics in the analog domain, which we can see this machine is actually is called Adeline. It's almost the first form of the neural network, which is built with a device called memristor. It's not memristor, it's a different concept. It's still a resistor with memory. And And however, the digital computing has become the dominant form of the computing in the recent decades. It has changed our lives entirely, and this has bigger impact than the analog computing throughout the history. The fundamental reason behind it is because I believe it's extremely easy to program for general purpose. And what's more, the Moore's law makes the upscaling of this computing machine effortless, and at the same time makes us lazy because we don't have to do any innovation to make the computing more powerful. The good point and bad thing is the Moore's law is finally coming to an end because we are approaching to like a 3 nanometers, 5 nanometer, which if we use that to build a transistor, is basically several atoms. So it's very, very challenging to continue the Moore's law as is used to be. So it's probably the good thing about it is because we got lazy in the past few decades, and we don't innovate too much. So it's probably now the time to give another thought on the analog computing, which is another paradigm of computing form. And one particular example that shows the digital computing is inefficient is artificial neural network. And because artificial neural network is not built for the digital domain, and the digital computer is very inefficient to emulate physics. Here in my talk, I'm going to introduce some works that use our device to emulate the neural networks. All the work are actually grounded by an emerging non-volatile resistive analog memory device, or we can call it a memristor, which is basically a resistor with memory. This is a very simple device with 2 electrodes, sandwich switching material, like a capacitor. What's different from the capacitor is that when you apply a large voltage across the 2 electrodes, the resistance or conductance can be tuned reversely. So take this particular device as an example. A large voltage across the electrodes will, for example, the large positive voltage across the electrode will turn the device from a high resistance state to a low resistance state. And reversely, if we apply a large negative voltage, it will tune the device to a higher resistance state. What's more interesting is that if you stop the programming process at some point, actually, you can tune the device to an arbitrary conductance state, so that you can have you can make the conductance states in the analog form. And what can we use? What can we use for this device? And first of all, we find this device can pertain the analog state inside of the memory, which means it's non-volatile, and which means it does not require a static power to sustain this conductance state. And second of all, we find that because they have multiple states, so that we can use this device to do some computing according to some physical law. And this can solve some computing problem. And what's more is that we can do some computing directly inside of this memory, so that you don't have to move the data back and forth to solve the data bandwidth problem. This device is a new device, and it also demonstrated it has a good scalability, and the switching speed is fast, so that it can support a large data size, which means combine all the 3 features, which is a large data bandwidth, efficient computing, and data size. It makes it ideal to make some computing machines more powerful. And I'm going to start with this figure to show how this device can be used to perform analog matrix multiplication. Basically, this device is organized in the crossbar form, which is that you have, for example, you pattern two series of electrodes. One is row wires, and one is the other is column wires. At each junction, you have a memristor device. In order to do the computing, you will need to convert the input vectors to analog voltage and then apply to the row wires. At the same time, you ground all the columns wires so that the current flows through each device. It's going to be the scalar multiplication of the corresponding voltage amplitude and the memristor conductance value. And the current is going to be summed up across the column wires so that if you do the math, you can find the output current vector is intuitively the voltage vector multiplies the conductance matrix. And in this computing form, we can find each cross-point memristor is actually a multiplier that compute in a massive parallel fashion. And also because it's parallel, so that you can compute the vector matrix multiplication in one step, regardless of the array size. And what's more appealing is that actually you are performing the computation at the exact location where the information is stored, so that you don't have to move the memory back and forth, and solves a memory wall problem in the current computing system, especially when, for example, you need to move the data from the DRAM, which is the case in the current like a neural network training problem. And this matrix multiplication is pretty important because you can find many applications such as artificial neural network and signal processing. In addition to that, I want to point it out this device can do much more than matrix multiplication only. Recently, we have also demonstrated this device can be used to build content aggregate memory that searches for a pattern in analog domain. Different from the matrix multiplication, this type of memory actually returns the location of the exact match instead of like a vague match. This function finds lots of applications such as like a finite state machine, accelerating tree-based models, etc. But this is just an example that this device can do much more than matrix multiplication. But today we are going to still focus on matrix multiplication because it finds most application scenarios that's more mature. In order to measure to demonstrate this device can be used for the matrix multiplication, we build a test chip. And we arrange the device in the 1T 1R form, which means each memristor is seriously connected to a transistor, so that we can use the transistor as an access device to program the device more accurately. But when we do the matrix multiplication, we're going to turn on all the transistors so to make a real crossbar and do the computation inside of the memristors. In order to measure that, we build an off-chip control peripherals so that we can supply multiple different voltage amplitudes at the same time, and up to 128 channels. And at the same time, we can also sense the current and values in parallel, and to demonstrate that this device can do something. And for our generation 1 platform, we are building all the control peripherals, including the digital to analog converter and analog to digital converter on a PCB board, so that but it has a drawback, which is it's going to be pretty slow because of the long RC delays between the board and the chip. But still, we can demonstrate this device is good enough for many applications. And here is shows a pattern that we program a Hewlett Packard Enterprise logo is in the array, which is a gray pixel. And each pixel represents a conducting state of one memristor device. And then with this platform, we are able to demonstrate this device can accelerate different type of neural network, including the convolutional neural network and the fully connected layer. And we have demonstrated that very easily that this platform can do the MNIST handwritten digit classification up to with accuracy above 90% pretty easily. But this is for inference, which means we program the pre-trained weights. We train the weights in the computer and then transfer the data, the weight into the memristor crossbar with this peripheral. And after programming, we are not going to change the device at all. But for most scenarios, for example, the edge computing, we don't have to change those values as long as it's going to be accurate. But I will introduce a little bit later that this is not an ideal situation, and there's like many more devices can have defects, so that we have to come up with some solutions to solve this problem. So the next part is CMOS-integrated nanoscale crossbars. As I introduced earlier, the Gen 1 chip is only a crossbar array without any peripherals on it. And we have to build off-chip peripherals, which introduce a large RC parasitic to slow down the operation. And also, because for the demonstration purpose, we build micro scale devices. They are large, but it's easier to fabricate. And here is shows our Gen 2 chip with integrated peripherals, CMOS peripherals, including the ADC and the sample and hold circuit and transient impedance amplifier and a lot of the signal routines directly on the chip. We use TSMC's 180 process node, and the memristors are built. The lateral sides of the memristors are 15 nanometer by 15 nanometer, and on each chip we include like different peripheral circuits and driving circuit, including the 10 bits ADC, and this entire chip works in under 15 megahertz, and we can do the compute and read operations within 140 nanosecond. At worst, it's apparently depends on the current level. For example, if we have a large enough current for doing some matrix multiplication operation, it can be much faster than this 140 nanosecond. And what's more is it has more than one array on this chips. They have tiled array, so that we can do some a little bit more complicated tasks to connect different layers together to for more advanced models. As I said, it's a little bit different because the device is in nanoscale, and this here is the fabrication process of this device. Basically, we fabricate, we take out the silicon circuit. Hello, can you still hear me? Because I find my
yes, I can still hear you.
Okay. Okay. Basically, we fabricate the silicon circuit in the commercial foundry in the front end technology, and we stop the entire process at the metal 6 layer,
and leaving a contact holes so that we can integrate the memristors on top of the silicon circuit. And this particular memristors we integrate has a tantalum as top electrode, platinum as bottom electrode, and which sandwich tantalum oxide as a switch layer. We have tried to fabricate the device from pretty large scale, about 1 micrometer by 1 micrometer, down to 20 micrometer, 25 nanometer by 25 nanometer. But what's interesting is we find this conduction range of this nano device is a lot larger than a micro size device. And for example, take this as an example, we can find this conductance can be tuned from as low as smaller than 1 nanosiemens to 100 microsiemens spans more than 10 to the fifth orders of magnitude. So that it enables us to operate the device to in a much lower conductance range, which means lower current and lower power consumption. And we also examine that this wide range phenomenon is actually dependent on the device size. Generally, if a smaller device have a higher yield to have a large conductance range. And because it has a conductance range, very wide conductance dynamic range, we measure the device statistics. For example, the number of device states is automatically determined by how stable the devices are. So we measure how stable the devices are when we program the device at a different state. And we find this stableness of the device is actually dependent on the conductance is programmed to. But we have analyzed the data, and if we carefully determine the boundaries of the each state it programs to, we can find the device can be potentially programmed with up to 8-bit accuracy if we define positive and minus 2 sigma as one discrete state. So it's much better than our previously micron size device already. With this device, we are able to demonstrate this platform can do a convolutional neural network directly on this chip, and we cascaded the convolutional layer followed by a fully connected layer directly on the same chip. This is the model structures. We have a fairly simple convolutional neural network model to help classify the MNIST handwritten digits. We don't downscale this device, this image too much. We just crop the device to from 28 by 28 to 24 by 24, and then we're gonna transfer the image data directly to the chips through the chip controller on this board. And this shows our measurement board. I want to point it out that actually for most part of it is for debug purpose instead of like actual computing, actual control peripheral. All the control peripherals are integrated inside of this circuitry socket. And we are also able to set up this platform in Hong Kong U campus, so that we were able to run some more exciting demonstrations with this platform. And here I want to show this is how we can classify handwritten digits with this chip. And as you can see that after I wrote write digits, it will send the data to the security chip, and then it will return the classification result. I also want to point out that most of the time is actually consumed during the communication process. So the actual communication is actually much faster than what's shown here. Without too much efforts, we achieved 95.3 accuracy on this chip, which is I think is pretty close to the software baseline, which is 97%. In parallel, we have some efforts to make this computing scheme more scalable, to have some efforts in the system architecture, compiler, and software stack to make the people easier to use this platform. And but this is not my work. I just want to introduce some work from the colleagues at the Hewlett Packard Labs. But it is gonna this work, I believe, is gonna make could be the key enabler of this technology, because for many technology it died because no one want to use it. And this work actually build a simulator based on the FPGA to emulate the different tiles of the memristor crossbars. And on top of that, it has a compiler so that it can compile the neural network specification in ONNX to convert a DPE specific assembly language to map those to crossbars. They have done some work to how to map those workloads more efficiently. And this is and what's on the right shows a complete stack of this development. So that basically the goal of it is to let the user to be transparent to the underlying implementation, so that if you in the future we have a mature the memristor crossbar platform, you can just use the same language like Keras, but use a different compiler to make it run faster. We have demonstrated this this DP platform can do YOLO tiny, which is a pretty complicated model with 11 million trainable parameters, and it's run on a quantized software model on the FPGA demonstrator. This is a architecture paper, and this talks about when we implemented this memristor crossbar, and we can see by the way, the Puma means is an architecture for this memristor crossbar. We can see the Puma architecture can do orders of magnitude benefit compared to the mainstream CPU and GPU platform. Although these demonstrations are very promising, I have to admit that it's far from there's still a long way to go before the commercialization. And one of the bottleneck is that the device is not very mature, so that it has a limited yield. Even for some demonstrations, it has a very high yield. It has some stability issues. For example, it can have some a random telegraph noise, so that to make the device fluctuate around the range. And also sometimes we can find the device states is drifted, and more drastically it can fail by fail completely to change the device state to another state. So so these errors can be categorized into three classes. The first one is intrinsic, and the second one, third one is temporary and permanent. And the goal of our computing platform is to tolerate such intrinsic computing error, but for some temporary or permanent error, we still want to detect or correct them, so to make this computing platform more mature. Here in the figure on the left, we use the experimental result of the analog errors by a crossbar, which is calculated by the difference between the expected output and experimental output. As we can see from the result, while most of the errors are quite small, there are still some significant error outliers. Although previously we have demonstrated that some algorithms such as neural network are quite tolerant of small errors, they're not to the significant outliers. The figure on the right shows that one significant device at a particular location can drop the MNIST classification accuracy from more than 90% to as low as 44%, which is fatal which is fatal. Therefore, this kind of defect we have to detect or possibly correct them if they occur. And it's only for neural network, and we know for sure that it's tolerant of defects, but this is going to be even more fatal for applications where the reliability and computer precision are demanded, such as like scientific computing. So for those applications, we this kind of like analog correction is more needed. So it's here I choose the error correction, the mechanism of the error correcting code. In the digital domain, the error can be is in digital domain. Actually, the error correcting code is widely used, especially in the scenarios where the noise and errors are frequent or data fidelity can degrade over time. The fidelity of the data that's stored in the ECC memory are usually higher, and as a result, they are sold at a higher price. So here we can see the benefit of the better reliability in something. And here's the concept of our analog ECC, and it's different from the ECC in the data communication, as I showed in the previous slides. And in some sense, in here, we can still see the transmission process in this computing process as a transmission, but it's a little bit different because this noise, this noise or the computing result is actually dependent on the input, which is a little bit different from the transmission process. And this is and here, what's on the left shows the mechanism, how this analog ECC works, which in essence is to add an encoder matrix close to the matrix for the real multiplication, so that it can compute the redundancy part in parallel with the actual computation result. And the other difference from the ECC in the digital domain in the transmission process is that it can tolerate a small error or the intrinsic error as I introduced earlier, and while only detect and correct the error exceeds a certain predefined threshold. This is pretty important for this analog computing because we don't have to talk because because if we detect the intrinsic error, then the detection is gonna happen all the times, and which makes the computation not possible. I'm gonna use some breakdown of the analog correction steps. This is an actual example to show how our scheme works. What's on the left is a matrix for multiplication. Here we denote as a way1. And before multiplying any vectors, we add additional columns that forms an encoder matrix to generate the redundance output at the same time. I want to mention that the encoder matrix needs to be configured only once for a given matrix. After the encoder matrix is configured, we can use the matrix to multiply the input vectors, such as U, shown in this figure. As a result, the actual output vector Y and the redundance output vector R are generated at the same time. The output vectors are weighted sum of each input row vectors of the matrix. So because of the design, the output shall preserve a specific relation designed in the choice of the encoder matrix so that we can use some other scheme to detect them. And this actual output combined along with the redundance output can be checked with a decoder matrix as shown here. And we call the output of the decoder matrix as a syndrome vector. And this is because this vector includes the information of whether the error has occurred and location of the error where the error is occurred. Because and from this figure we can see that because the output vector preserve a specific relation designed in the choice of the encoder matrix, if there's no error or there's only the intrinsic error within a predefined threshold in the multiplication process, the decoder output should be within a predefined range so that no error is detected. But in case of one significant error, let's say in one column, the corresponding column pattern in the decoder matrix will be added to the result, leading to a considerable deviation from zero output. So that we can look up this particular pattern inside of the decoder matrix to identify where the error has occurred. In this case, for example, we can find the location of the exact threshold is read as 0, positive 1, 0, negative 1. So it matches the fourth column here, and so that we know this error occurs in the fourth column in this output. It can be some added noise or some stuck device inside of the crossbar. So and also here we can show some plausible hardware implementation so that this entire encoding and decoding process does not impose too much additional overhead. And it has 3 parts. One is a 4-part, primarily 4 parts. And the first part is the actual matrix for the multiplication. And second part is an encoder matrix. And third part is a decoder matrix, which is also a crossbar. And the fourth part is all the peripheral circuits, which we don't foresee to be a very large overhead. And to demonstrate this idea, we program some pattern inside of the integrated CMOS-integrated platform, as I introduced earlier. And with this integrated system, we are able to program any matrices in the crossbar arrays. Here, I show an experimental readout connectance matrix. after programming both matrix for actual multiplication and the matrix encoder matrix. The matrix value are mapped to the connection value between 0 to 100 microsiemens in order to simulate the case where one device was significantly disturbed. For example, the stack device, we program one device on the top left corner to a very high connected state, as shown here. As a result, the computing statistics show a higher probability of a large error, which is shows this in this blue curve. But after the analog correction, we can see here the chance of the significant outliers is significantly reduced. This emulates the case that the device is permanent, the defect in the device is permanent. In order to demonstrate the effectiveness of this scheme, we apply this in a convolutional neural network to classify the MNIST handwritten digits which is the same as the previous demonstration, but what's different is that we intentionally program one device to a very high resistance connected state to emulate the stack count case. And we can see this result on this plot that with one device was intentionally programmed to a very high connected state, the MNIST classification accuracy dropped to 90%. After the analog ECC, the accuracy can be recovered to 96.21%, which is pretty close to the software baseline, which is 98.20%. Additionally, we emulate the case where the noise are transient, which is in this case the noise or the analog error is added to the output node inside of the conductance matrix. In order to emulate the case, we program some actual device in a specific column, and then apply the voltage on the corresponding rows to inject the noises. As we can see that before the analog ECC, because of the injected noise, the experiment output is deviated from the expected output. But with the analog ECC, we can cover most of the errors. But we can still see some small portion of the errors because there's like a statistic behavior, and also because of the encoder matrix is not perfect, but this still shows this scheme is good enough to recover most of the error, and more importantly, and the effectiveness can be used to demonstrate in this convolutional neural network. As we can see from this data, with some injected noise, the accuracy dropped to like a 73%, which is pretty bad, and it makes the neural network not usable at all. But with the analog ECC, it can be recovered to 97.36%, which is even higher than the noise-free scenario. In this case, I think this is because this scheme can correct, in addition to the injected noise, we can also correct some intrinsic outliers, which is resulted from the device wire resistance, IV nonlinearity, etc. So in short, although as we can see from this plot, some of the errors are not corrected, but we can additionally correct some intrinsic error so that the accuracy is even higher than the noise-free scenario. But the ultimate goal of this scheme is not to boost the accuracy, but to increase the reliability of this computing platform, so that for example, if there's a permanent error that occurs, we need to notify some controller in this system that some array needs to be reprogrammed. So, but luckily we are able to identify the locations of the columns that the errors occur. And for this like a temporary error, we don't need to like reprogram this array, but we just need to what we need is just to run this computation for another time to minimize the error. And there's a intrinsic trade-off between the number of encoder matrix and encoder columns and the degrees of the error detection. And so in short, if we want a higher accuracy, then we need a more larger area in the encoder matrix. And also, but if we want to like save the hardware overhead, we can just release that requirement to detect only the significant outliers, and we can save the overhead even more by a program by like configure this matrix to error detection only mode instead of like a detection plus correction. But even with this error correction, there's still some like errors that can not be fixed with this scheme. And also with this scheme, what we can do is only the inference. But intrinsically after the inference phase, we ask ourselves, can we do the training in the neural network? And the nice thing for the training itself is that in addition to the training process, in addition to the additional functionality, it can also adapt the defect inside of this computing array. It's not only like for the device defect, but also the peripheral defects, as we can see, we can show later. So here shows two lines how the training works. So in the training, there are like two phases. The first phase is the same as what I introduced earlier. It's an inference phase, and then because there's because the connected states are not programmed to what we want, and it will cause the output different with the expected output, so that we need to adjust the connectors correspondingly to make the output more accurate. And this there are like two phases. As I introduced, there are two phases in the training process, and if we break down the process, we can find there's for the signals there are forward propagation and the back-propagation. And the backward propagation is actually the multiplication with a transposed matrix, but this step is actually very difficult to be accelerated with conventional accelerators because you need to move the memories inside of the chip. But with the memristor crossbar, it's pretty intuitive because instead of moving the memories locations, you can do this backward propagation intrinsically by applying in the errors on the column wires, and then read out the previous layer delta on the row wires. So that is an intrinsic reverse process. And there are like several like architecture efforts in developing this training process. But those interactions only occurs in the ideal world. But if we measure the device, we can see there's a pretty large device variation. If we take only one device as an example, we can see that this device transition curve is pretty smooth and transient. But the problem is this device variation is too large, which means in order to get this very nice curve, we need to very carefully to adjust the the pulse amplitude and pulse width. And we have also tried some other scheme to make it better. For example, to increase the pulse amplitude as the device conductance changes, but the device-to-device variation is still too large to make the scheme works. And what's more is that we can find this transistor is not linear, which makes some of the training process not feasible. And so we have, so basically there's intrinsic noises inside of it, and how to deal with it. So if we cannot deal with it, we can exploit it. For example, we can use exploit the intrinsic nature of the stochasticity to find minimum energy, or to do some hardware security applications. But finally, we have to solve it. And our solution is to lies inside of this 1T1R device. And because our device is already integrated with a transistor, so my question is, why don't we just make use of it? And when we program the device, as we can see here, we have already found that the conductance, the conductance state of the memristors device is always matching with the conductance state of the transistor. So that in a certain range, the conductance state is linearly dependent on the conductance value of the series connected transistors. So if we make use of this phenomena, we are able to tune the conductance back and forth, and with a very good device to very small device to device variation and very high linearity. And this process in essence is trying to minimize the device stochasticity lies intrinsically in the memristor device, but to employ the good uniformity in the silicon transistor device. And with this scheme, we are able to train the MNIST data set pretty good. And here is the animation which shows that how these weights are changed. Each pixels in this animation is actually represented by two memristor conductors with difference of the two memristor conductors. But as we can see, is that there's some noises in this transition, but it is still good enough to train the network to higher than 90%. And I want to point it out that in this array there are 11% of stack off device, but we can still achieve the accuracy larger than 90%. And also we have evaluated the case that if the peripheral circuit suddenly change or the conductance states suddenly change, that's going to be fatal for like many inference problem. But what we can do is to train the network, even if it's only the last layer, but after a few iterations, it can recover the accuracy to what to the time before the error occurs. We compare this training algorithm with the TensorFlow, which is a software baseline, and several different simulation framework to simulate the device has 11% of stacked device. We can see that the simulation matches our experiment pretty well, and it's not a lot different from the TensorFlow baseline. And here shows the example where the in-situ training can compensate even more defects devices than the acceleration training. And for access training, which means inference only, and I have already introduced that these defects can be detected and corrected with analog ACC scheme. In order to make this scheme works easier, we have developed a Keras-like machine framework so that we can demonstrate the training of the different tasks more efficiently. And we have demonstrated that this network can be used to recognize the human walking style, to identify the human by the style of his walking, and also to demonstrate that the memristor crossbar can play the games with reinforcement learning. And so this is the last slides of my talk. In summary, we have operated directly with integrated CMOS and nanoscale memristor crossbar. Integrated CMOS peripherals makes the operation faster because of the smaller RC peripherals, and the nanoscale memristor crossbars enables a wider connectors range, which means this platform can be computed with smaller power consumption. And also but there are like several device defects because of the device itself is not mature enough. We come up with a solution, two solutions. The first solution is analog error correcting code, which can detect and correct error outliers within some like mathematical calculations. The second way of doing that is the intrinsic in-situ training. And the best thing about it is that we can train only the last layer to compensate most of the device defects. And I would like to thank my colleagues and advisors at the Hewlett Packard Labs and MNIST, and as well as a lot of collaborators. Please feel free to ask questions. I believe this is going to be the Q&A section.
Okay. Thank you, Professor Ni, for the wonderful seminar. It's very inspiring. Now it is the Q&A time. So you can raise your hand and I will ask you to speak up in sequence, or you can just type your question in the chat box and I can ask on behalf of you. Okay, I see Vincent No has, okay, turn on camera and microphone. You can ask question.
Hi, thank you. I try to raise my hand, but I don't know where is the button. So let me just speak up. Thank you. So thank you, Professor Lee, for this interesting talk. I do not work on device, but I work on the algorithms and system side. So I'm curious. I actually have two questions. So in your first part, I mean the middle part of the analog error correction, I try to turn to the page on the analog error correction coding.
Yeah, sure.
Yeah. Okay. So I try to understand what do you mean by error. So your input is U, a vector U, right? So this vector U, is it digital or analog?
Yeah, analog.
It's
analog.
Okay.
Yeah.
So now after you multiply,
it's a real value.
After you multiply with A1, so you get this Y, right? The matrix rotation, and then you also generate the redundancy R. So when you say error, what do you mean by error?
Which means, for example, if there are like for example, the Y equals U multiplies A, right?
Right.
So if some elements in the A got this is like a suddenly changed to another state, then the Y is not going to be the expected output because the A has changed.
So you mean the error is on the Y output?
Yes.
Okay.
Exactly. But it can be resulted from multiple causes. For example, the device error or the injected noise, like injected current noise in the peripherals. So it can be added out directly into Y. In that case, the error is not dependent on the input. And the other case is that it can occur in the A. In that case, it's going to be dependent on the input.
So what do you assume? You assume A1 may be prone to errors, but what about A2, the redundancy?
It's the same thing.
So it's
The same thing. Yeah.
Then in your syndrome computation, do you also have errors in your syndrome?
Yeah, possibly, yes.
Then how can you possibly detect errors and correct for errors?
Yeah, but just because of it's a matter of probability.
Mm-hmm.
Yeah. So this is why, as you can see here,
Mm-hmm.
this error correction is not perfect.
I see. Okay. So
yeah.
Okay, because in information theory, our input is binary digits, and then we talk about under what condition you can for sure correct for whatever number of errors. So
yeah,
that is
yeah. This is a very good question. I think the next step we want to do is to quantify the effect of the error correction, because it's not surely not 100%, but it's still good enough for many neural network applications.
Right. I see.
And also the nice thing about it is that the redundancy output calculation is at the same time as it occurs in the same time as the actual modification takes place.
Sure. Okay, that's good. So my other question is regarding the training, your final part. Can you turn to the slides of the training? So where you have the forward and backward propagation. Right. Okay. So I'm also confused how it works. So now my understanding is the G, the conductance matrix, is like the weight of the neural network, right?
Yes.
And the B is like the data input, and the I is like the data output after the first layer of matrix modification. That's the inferencing. But now in the training, what you want to do is actually to adjust the conductance, right? Suppose you do stochastic gradient. So, but then in your illustration here, it seems like your conductance is not modified, but then you just modify the X and Y.
Oh yes. This is because it's here I'm not. So in the training process, actually there are like 3 steps.
Right.
The first step is the forward propagation, so that you can calculate the output based on the current weight matrix.
Right.
And the second step is to calculate how much we want to change the weight. Right. But this step is not about update the weight. It's about to calculate how much we want to update the conductances or weight values. And this step, in order to do that, we need a back propagation process.
Right.
And the back propagation, which is to calculate the deltas, and the calculation is illustrated in this equation, so that you need to calculate the deltas for each layer by multiplying the conductances, the transpose of the weight matrix, and the delta in another layer.
So after you get the delta X, then what do you do with the weight?
Okay, we need to update the weight, update weights data. There are still 2 steps. The first step is to calculate the delta W, and then apply the delta W in the device, to the device.
Right.
But in this step, this is still pretty computation intensive step.
Yes.
To calculate the delta W, because it's O n squared as well.
Right.
But this step is outer product, and we are currently implemented. This step is currently implemented in software, but we can potentially implement this step in hardware by encoding this information in a probability form, so that the magnitude of the conductance change is proportional to the probability that the input and output overlaps. It's a little bit we have some discussion inside this paper, in the pencil paper.
Right. I see. So
we have not implemented experimentally yet.
I see. So now So I suppose you're doing stochastic gradient, right? So which step
Yeah.
you compute the gradient?
Mm-hmm.
In the step, which step you compute the gradient?
Oh, after the back-propagation.
So that means that after you have the delta X, how do you compute the delta W? This step you need the gradient, right?
Yes.
And that is the step that is still not yet implemented in the analog computation,
Correct.
as you just mentioned. I see.
Correct.
Okay. Right. Okay. I see. Thank you. Thank you very much.
But I think the
Right.
key point of this training process is not about to accelerate the training, because we can see a lot of challenges, as you mentioned, that there are like many steps that's not implemented in the hardware. But the key point of the training is to adapt the defect
Right.
in this analog computing. So the application scenario is still the inference.
I see.
So I think the more realistic scenario is going to be make the last layer trainable, but with additional hardware overhead. But we can, but in that case, we have to do some training directly inside of this crossbar.
I see. Okay, thank you.
Thank you. Very good question.
Okay, so we have a few questions in the chat box. So one from Yang Chai. So Yang Chai, do you want to just speak up and ask a question? Or you want me to ask on behalf of you? Okay, maybe I can ask on behalf of you. Okay, Yang Chai asked, okay, how to understand the data bandwidth similar to the wavelengths in optical computing?
Data bandwidth?
Yes, how to understand the data bandwidth similar to the like wavelengths in the optical computing?
I'm not very familiar with optic computing, so I'm not sure if I'm qualified to answer this question. So because I'm not sure how to compare with optical network. But I think in many cases it's pretty similar to the optical neural network, because it's this computing element, which is a memristor device here, is a passive element. It's not a and it's similar to many optical neural network, which means this like a different lens, only do some dimensions of the input signals. But for the bandwidth, I think is I think we should compare. Probably we want to compare the RC with the optical bandwidth. In that case, this throughput is going to be much smaller than optical counterparts. But the benefit of our electronic devices is that we can have much higher integration density, because optics will have to struggle with the limited scalability, because they can only make large device, but they can have more like a parallelism, I think, because they can process like information in different bandwidths at the same time. The detailed trade-off is going to be a further study. That's my point. That's my view. I'm not sure.
Okay. There's a lot of question from Zheoyang Zheng. Okay. So Zheoyang Zheng, do you want to ask directly? No. Okay. So on page 12, okay, what does the gate voltage mean?
Okay.
Is it a 3-terminal device?
No, it's a I'm trying to find the restriction. Wait a minute. So this device is actually arranged similarly in this configuration. It's not a 3-terminal device, but it's a 2-terminal device that connected in series with a transistor. The gate voltage means the gate voltage applied to the transistor gate during the set process. And the reason why we can get this relationship is because this voltage dividing effect, and you can do some math to assume the set transition is a transient process, and you can easily get this equation. And
okay.
I hope it's clear.
Okay, so the follow-up question, actually, this is also a follow-up question from me, okay? So in this case, the gate controls the conductance of the memristor, so somehow.
Yep.
Okay, so in this sense, you can make it a very linear, programmable.
Yes.
I see.
And here shows these two figures actually shows a case that the program as a memristor is programmed without the transistor, which means the transistor is fully turned down. And we can see with identical pulses and increasing pulse amplitude. Although if we pick like a single device, it's going to be very smooth and transient and gradual. But if you like make all the curves together, you can see the device to device variation is too large, which is I think not the data that you're really seeing in some paper. But so that's why in order to make this demonstration, we have to make use of the transistors for the training process. But for inference, we just program the device iteratively, then that's better.
Okay, so the follow-up question to Yang Chai's question is like this. Okay, I think Yang Chai's question is about slide 4. So can you go to slide 4? So in which the speaker mentioned the data bandwidth. Okay, so could you explain a little bit more about this?
Okay, so I think I was not very clear, I guess. It's not about like you can increase the data bandwidth, just because the modern computing workloads have several bottlenecks. One is like the computing power is not enough, and the other problem is the data bandwidth is limited. But with this memristors, we can process information directly in the memory, so that it combines the computing unit and the memory unit, so that we can solve some data bandwidth problem because we don't have to move the data back and forth. But of course, if we want to use this memory device as a memory only, it can reduce the data bandwidth problem because it has a very large integration density, especially when the device is integrated three-dimensionally. Like for example, on top of the silicon logic, because it's backend compatible, which is not possible with many other mature semiconductor memories. But my point here is that it can do the memory computing, so that it can solve some data bandwidth problem in the computing workloads.
Okay, so the next question is this. Could you talk about how to evaluate and model the energy consumption for the defect tolerant in-memory analog computing? So
okay,
yeah.
Mm-hmm. Okay, this is going to be dependent on the how you implement this analog error correction. So if we use just for now, we just if we don't talk about the analog error correction, but only to talk about analog detection. So it's very intrinsic. It's intrinsically to see that the analog and speed overhead, the energy overhead is the added encoder matrix and decoder matrix. and it's going to be roughly proportional to the area that it adds to. And for the latency overhead, it's going to be roughly 2 times, because you need to go through the settling time of the transimpedance amplifiers again. So it's basically, it's going to be 2 times in latency, and because of the decoder step, but still, it's still tolerable if you have a much better reliability, and also in this, and also the in terms of the power consumption overhead, it depends on the added redundancy column, and it depends on how accurate the computing output you want. So in short, if you want to much better computing accuracy, you will have to endure larger power consumption overhead. That's a trade-off here.
Okay, so any other questions? So maybe I ask one last question. So you have already mentioned your first generation, second generation. So what is your like a third generation RM chip? So do you have anything in your mind?
Not yet. Probably we can, like, if we can use some funding, so maybe we can do something about it. But it's gonna be costly. It's probably have to seek for some collaboration from the industry partners, and most likely, I think it's gonna be the industry partner develop the platform for us, and we're gonna run some interesting ideas on this platform. We as in the academia, I'm not sure how feasible it is to develop such a platform, especially when it gets mature and mature.
Okay, thank you. So if no further question, I think that's all for today's seminar. Okay, I will stop recording.
Thank you.